now we will start week 7 of this course, and in the last 3 weeks we had a fairly intense discussion on the symmetries of crystals, and the discussion was quite intense and quite at times fairly mathematical, and as I had mentioned that sometimes these are not very easy to visualize, and you need to practice by looking at models and various solved examples. Okay. So, but now in the next few weeks we will change the topics a little bit. We will not talk about symmetries, but we will start talking about different aspects of crystals. Okay. So, today in this lecture and this week we are going to talk about coordination number and defects and packing in crystals. Okay. So, week 7 lecture 1 I will talk about coordination number and voids. Now, you are somewhat familiar with these terms like coordination number and voids. You might have seen them in your earlier discussion of solids. Okay. So, so some of this will seem like a revision, but it is always good to think about these concepts again. So, let us ask, what is the coordination number? So, the coordination number, first we will talk about coordination number of atoms in a crystal. Okay. So, if you have an atom in a crystal, then its coordination number is simply the number of nearest neighbor bonds that atom has. So, you just count how many other atoms it is closest to, okay, and that number will be the coordination number. The important point is that you have to look only at the nearest neighbors. Okay. Now, if you had a monatomic lattice like an FCC with a single atom basis, okay, then the coordination number of all the atoms will be identical. So, all the lattices, monatomic lattices, because each lattice point is identical, okay, each lattice point will have the same coordination number, and if there is an atom at each lattice point, then that atom will have the same, all the atoms will have the same coordination number. Okay. Now, the coordination number is of atoms is usually largest for close packed structures, and we will see examples of that. And you know, each atom in the crystal can have a different coordination number, okay, and you can look at individual atoms in crystals and look at their coordination number. Okay. So, for example, you would have a coordination number for sodium and a coordination number for chlorine in a sodium chloride rock salt crystal. Turns out that both of them have the same coordination number in this case, but you can imagine there are cases when the constituent atoms will have different coordination number. Okay. Now, so really what at the center of this whole discussion is the idea that you have some atom in a crystal, and you are looking around that atom. So, you look around that atom and you look in various directions, and you look at the other atoms that are around it. Okay. So, this is a very central idea that you imagine that you have an atom in a crystal and you are looking at all the other atoms around it. Okay. So, this is the generic idea of coordination number. Okay. And let me say that this is a very general idea, and therefore, you can apply it to several other objects other than just atoms. Okay. But the other point I want to make is that as a chemist, you know that this atom in a crystal, okay, if there are two atoms in a crystal, they are going to form some sort of a bond. Okay. There will be some sort of a bond between these two atoms. Okay. I will just show it this way. So, there will be some sort of a bond between neighboring atoms, especially if they are closest to the nearest neighbor. Okay. So, there will be some sort of bonds. Okay. So, you expect some sort of chemical bonds between atoms in a crystal, okay, And so, the coordination number is really a combination of the chemical bonding that these two atoms have and some size. Okay. So, let me emphasize that this point, it will become clear as we go along. So, both size of atom and should I say, I can say the nature or the bonding of atoms affects coordination number. And this is again a very, we will come back to this a little later. You know, we often in our picture of crystals, we like to visualize atoms as solid spheres. Okay. So, atoms as solid spheres, but really the way they bond, okay, it is not obvious. I mean, you have to look at the valence orbitals of the atom, and you have to see what is the hybridization that it can have, and only then you can decide what kind of bonds it forms. Okay. So, I will just leave this point here, that the simple picture of atoms as spheres is not adequate, and we will see it inadequate. We will see it very often that you know, just thinking of an atom as a sphere and all these spheres as packed together is actually fairly limited, but it is still a useful concept. Okay. It is inadequate, but still very useful. So, this is a point that I want you to keep in your mind, that you know, we will often treat atoms as though they are just spheres, okay, and we will do various calculations. Okay. So, you might calculate things like packing fraction or the size of the void, where you explicitly treat atoms as spheres. Okay. And in principle this is not adequate, and we will see soon why this is not adequate, but it is still a very useful and very powerful idea. Okay. So, let us look at some examples. Let us look at the very simple lattice, monatomic lattices. So, if you have FCC, okay, then what is the coordination number of the atoms? Okay. So, here you can see that in an FCC, I will show one conventional unit cell of the FCC, the cubic unit cell. Okay, with the atoms at the corners and the atoms at the face centers. Okay. Now, what you can see from this, and it is more clear if you extend the lattice, is the following, that let us take, I'll just take this atom that I am coloring in light green, and I will look at the coordination around it. Okay. So, if you look at this atom, the atom that is nearest to it is actually this atom. Okay. That atom is a distance, if this distance is a, okay, then this distance is a root 2 by 2, okay, because the diagonal, the phase diagonal is, the total length of the phase diagonal is a root 2, and so this is half of the phase diagonal. So, the distance between these two atoms is a root 2 by 2. So, that is this distance. Okay. Now, this is the closest neighbor for an FCC. Okay. And now let us take this out and we will see where else. Now you can immediately see that there will be one in this, in the same plane, okay, but in neighboring unit cells. Okay. Then we also notice that this atom is the same distance away, this atom here is also the same distance away, that is at the center of this face, that is also a root 2 away. Okay. Similarly, this atom in the center of this face is also a root 2 away. Okay. And what you can see is that in one plane, if you take this central atom, okay, so in one plane, in the in let us say in this plane that I will shade in a slightly different color. Okay, this plane, and you imagine that this is extended to many structures. Okay, so you have so the central atom has 4 nearest neighbors, but then there would also be 4 nearest neighbors in a perpendicular plane like this, that is perpendicular to the screen of the paper, and then there would be a third plane also where there would be 4 atoms, and that would be in the plane of the screen. Okay. And you can see now that basically there are 12 nearest neighbor atoms. Okay, so the coordination number will be 12. Okay. Again, it's you can draw the different planes. So there would be one that is the plane of the screen, and the third plane would be perpendicular to this. Okay, so you can easily see that there are the central atom has 12 of these atoms as the nearest neighbor. So coordination number equal to 12. And since FCC is a Bravais lattice, every atom is identical. So the coordination number of every atom is 12. What about BCC? Again, in the case of BCC, again you can easily see that in fact it's BCC is you can see it very easily, because if you take the central atom, the atom that is usually represented as the center of this cube, you can see clearly that it has 8 of these cube corners which are the nearest neighbors. So here you can see coordination number. Okay, so FCC has higher coordination than BCC. Okay, this is FCC, this is BCC. Okay, what about simple cubic? Simple cubic, you can see that the coordination number will be 6. Because in this case now each atom will have 1, 2, 3, and then it will have 11, 4, 5, 6. So each atom will have 6 nearest neighbors. So in simple cubic, I will write coordination number equal to 6. Okay, so the coordination number increases as you go from simple cubic to body centered cubic to face centered cubic. What about the HCP? So HCP you can see fairly easily. I won't do this in detail, but you can see that HCP, the coordination number is 12. Okay, and to see this, you just imagine that you have this hexagonal plane that is perpendicular to the screen, and you have another hexagonal plane that is perpendicular to the screen. Okay, and if you imagine the center of this, yeah. So if you imagine that now you look at this central atom, okay, and keep in mind that you have 3 more atoms here in the halfway between, okay, and you'll have 3 more atoms the top face above it, okay, and you can see that this central atom in red is coordinated to 6 other atoms in the plane, and then it's coordinated to 3 of them here in this direction and 3 of them in this direction. So, coordination number is 12, okay, and you can show that indeed for each atom the coordination number will be 12. Okay. What about our favorite diamond cubic structure? So, for diamond, okay, the coordination number is just 4 for a diamond cubic structure, and you can see this because each atom, okay, is will have only 4 nearest neighbor atoms. So, for example, if you take let us say the typical diamond cubic structure, okay, and now an atom in a diamond cubic structure, let's say you take this atom that is 1/4 along the body diagonal, okay, that will be coordinated to this corner atom, it will be coordinated to this face center, this face center, and this face in the face that is directly in front. Okay, so there will be 3 of these face center atoms, okay, and this corner atom. So, to all of them the distance will be 1/4 root 3. Okay, so these are fairly basic exercises, and many of you are already familiar with these exercises. Okay, so now let us go to the next topic, that is the packing fraction, and again I will come back to the idea of bonding in crystals. Okay, and now you have probably seen how to calculate packing fractions of crystals. Okay, so let us take the example of BCC. Okay, so in BCC we say that if you look at the structure of BCC, you have a cube, and you have an atom at the body center. Now, this atom at the body center, okay, let us draw it as a sphere. I am deliberately drawing it a little big. Okay. Now, this atom, okay, it is coordinated to all these, it is nearest neighbors with all these other 8 atoms, all the other 8 atoms at the corners of the cube. Okay. So, therefore, since it is closest to all these, okay, we can now imagine that this is a sphere, okay, and it is a sphere that is large enough so that it just touches all these spheres of the same size that are located at the corners. Okay, so there is another sphere at this corner. These are all supposed to be the same size, okay, same size, and they are supposed to be spheres. Okay, and similarly it will touch, it will be in contact with this sphere at this be in contact with the sphere here. Similarly, it will touch this sphere, and it will also touch this sphere from the, it will be in contact with this, and similarly it will also be in contact with this. Okay. So, really this is in contact with all these atoms, it's also touching this atom all the way behind. Okay. Now, what is what is important is that if you look along the body diagonal, okay, if I just stretch out the body diagonal to a straight line, okay, so the length of the body diagonal, if this lattice size is a, then the body diagonal size is a root 3. So, if you take this distance a root 3, you have this corner atom, you have this one atom at the body center, and you have this other corner atom, and this distance is a root 3. Okay. And if the radius of this sphere is r, okay, then you immediately conclude that 4r equal to a root 3. Okay, you conclude that 4r equal to a root 3, and now what you say is that in this BCC, in this cube, there are two spheres. So, volume of sphere into, so 2 into volume of sphere is equal to 2 into 4 by 3 pi. Now, r cube I will write as a root 3 by 4 cube. Okay. So, the volume of atoms, okay, so we say that the volume of atoms is this number, this quantity, okay, and that is, so if you write, you can write this as root 3 pi by 8 and multiplied by a cube. Okay. And the volume of cell is equal to a cube. Okay. So, this implies the packing fraction is equal to root 3 pi by 8, okay, that is about 0.68. Okay. So, the packing fraction of this cell is 0.68. That means, in this whole cube corresponding to a BCC to a monatomic BCC lattice, okay, the volume occupied by the atoms is about 68%. Okay. Now, what about FCC? Okay, for FCC, okay, now in the case of FCC, the atoms along the face centers along the face diagonal will be touching each other. Okay. So, and then there are 4 atoms. Okay. So, if you put it all together, you get a packing fraction that is given by 4 atoms, and the volume of the atoms of each atom is 4 by 3 pi. Now, r cube, r will be a root 2 by 4 instead of root 3 by 4. Divided by a cube. So, this becomes equal to pi root 2 by 6, okay, and that is equal to about 0.74. Okay. So, the packing fraction in FCC is more than that in BCC, and we say that FCC is closely packed, is a close packed structure, and also HCP we have packing fraction of 0.74. Okay, and FCC and HCP, they represent the closest packed structures for a single atom structures. For crystals made with a single atom, this is the best packing fraction that you can get, or this is the highest packing fraction that can be obtained. Okay. Now, in this whole calculation, you notice that we have treated these atoms as spheres. In fact, we have treated them like hard spheres, okay, that just touch each other, and they like here you can see that they are just touching each other, okay, but they are not going into each other, they are not distorting. Okay. So this picture inherently assumes that these atoms are spherical object. Okay. Now, as I said, this is not exactly correct. I mean, atoms do have electrons which have orbitals and which can have shapes, and so it is not like spheres that are touching each other, because there are orbitals and there is overlap between these between the orbitals of the atoms. Okay, and this is a reason that though based on the packing fraction, you would expect that most structures would be FCC and HCP, and that is correct, but you do occasionally find BCC structures to be more stable. Okay. So the point is that occasionally BCC is more stable, and what I mean is that you see the element forming the BCC structure instead of the FCC or HCP structure. An extreme case where the bonding, okay, so in this case we have assumed that bonds are not directional, okay, which is largely true for metals. Okay, so in calculating this in this whole picture of how the atoms are packing into the crystals, we are somehow at the back of our mind we have this picture that the bonds are not directional, and this is largely true for metals. Okay, so this is okay for metals to some extent. Okay, so therefore most of the metals crystallize in FCC or HCP, okay, but not for non-metals. So definitely silicon crystallizes in a diamond cubic structure, okay, and if you calculate the packing fraction of diamond cubic, it will be much lower. In fact, the coordination number is only 4, so the packing fraction is actually only about 34%, okay, and that is also found, okay. And that has to do with the fact that the bonds in diamond are really covalent bonds that have a very specific direction. Okay, we will keep this in mind as we and then move ahead with the discussion. Okay. Next, we will talk about voids in crystals. Okay, the voids are actually these refer to empty regions in a perfect crystal. Okay. And if you take the example of FCC, okay, we'll first take the example of FCC, and then we'll introduce the idea of coordination number of a void. Okay, so we'll show that even the void, okay, which is not an atom, okay, you can also talk about coordination number of the void. Okay, we'll start with FCC and then we'll do the other. We'll look at some other structures. And at this point, let me point you out to this website. Okay, this is my colleague and Professor Anand Subramaniam from the Material Science and Engineering Department at IIT Kanpur. He has an e-book, and in that he has an e-book on Introduction to Material Science and Engineering, and in that there is a very nice presentation that is put up on voids in crystals. Okay. And this really explains these ideas of voids extremely well, and I encourage each of you to go and look at this link, and you'll understand the idea of voids very well. Okay. So let us get back to the FCC. Okay. Now you might have learnt in your undergraduate or perhaps even in high school that the FCC crystal, a perfect FCC crystal, okay, has some regions in it, okay, which we refer to as voids, okay, and these have some very specific regions which we call as voids. Okay, and let me just show the atoms. I won't show the atoms as touching each other, but really you should imagine that these are large spheres that are touching each other. One right in the center of this face. Okay. Now there are these regions. Okay. Now the two kinds of voids, I will show one of them in this light green color. So if you take the center of this region, okay, okay. Now the center of this, at the center of this you have something called a tetrahedral void. Okay, so this is located in the center of this region. Okay, and now this point in blue is equidistant from this face center, this corner, this face center, and this face center. So this last one in red is actually located in the face directly in the plane of the screen. This point in blue, okay, is equidistant from each of these 4 points, okay, and this is referred to as a tetrahedral void. Okay, and this coordination number is actually 4, coordination number of the void. Okay, so this 4 is the coordination number of the void. Okay, and you can have tetrahedral voids. So this is closest to this corner atom. Okay, and since there are 8 corner atoms, you can have a total of 8 tetrahedral voids. Okay, so in this conventional unit cell you can have 8 tetrahedral voids. Okay. Now there is another kind of void which is called the octahedral void. Okay, and I will show you one of them. Okay, one of them is located right in the center of this cube, okay, and that is coordinated to, it is equidistant from each of these 6 face center atoms. Okay, so the octahedral void, okay, 6 is the coordination number, and now if it is located at the face, if it is located, you can locate it at the center of the cube. You can also locate octahedral voids at these edge centers. Okay, so this would also be on an octahedral void, because it would be connected to, it would be coordinated to 6 atoms. So now there is one at the center of the cube. Okay, and there will be there are a total of 12 edge centers. Okay, and each one contributes 1/4 to the cube that we are looking at. Okay, so total of 4 octahedral voids. octahedral voids. So, in this one conventional cube that we consider, okay. So, with respect to this cube, there are 4 octahedral voids and 8 tetrahedral voids, and you should keep in mind that this cube has 4 atoms, okay. So, now what is interesting is that you can ask a question, you can ask the question about the size of these voids, okay. Since just as we looked, we can look along we can take a line from this corner atom to the void atom, and if you imagine that there is a little sphere out there, okay, then we can find out the size of that sphere that will fit into this void, okay. And if you do that, okay, it is again very simple geometry to find out the size of the void, okay, size of voids. Okay. So, for tetrahedral, okay, you can easily show that the radius of the void divided by radius of this atom, okay, radius of this atom, okay, this is equal to 0.225. For octahedral void, you can easily show again that the radius of the void divided by the radius of the atom, okay, this is about 0.414, actually it is root 2 minus 1, so it is 0.414. Okay. So, therefore, what you conclude is that the size of the tetrahedral void is smaller than that of the octahedral void. So, the tetrahedral void is smaller than the octahedral void. Okay. So, you would expect that only smaller atoms would go into the tetrahedral voids and the larger atoms would go to the octahedral voids. Okay. And again this picture is assuming that the atoms are spherical objects, okay, which they are not, and in fact we will show that you do have atoms going into tetrahedral and octahedral voids which do not satisfy this ratio. Okay. What about voids in BCC and HCP? Okay, again I will not go into this in too much detail. You can look at the website that I pointed you out to. Okay, but you can show that in the BCC, if you take a conventional cube of the BCC, with an atom at the body center, okay, then you can show that these points will be octahedral voids. Okay, so each of the face center, the points at the face centers would be an octahedral void. Okay, it would be coordinated to the central atom. Okay, but there is a little bit of a catch. Okay, and this is the catch that you get with BCC. Let me explicitly show the atoms that are around this void, and there would be one above it. Okay. So, this is what we mean by an octahedral void here. Okay. Now, it is actually, this is slightly distorted. Okay. The reason we say it is distorted is because this length, okay, so this side, okay, let me show it in a different color, this side in blue. Okay, so the distance of this void to this atom is a by 2, okay, whereas the distance to this atom, to any of these atoms, is a root 2 by 2. Okay, that is half of the face diagonal. Okay, so if a is the side of this BCC cube, okay, then this distance is a by 2, whereas this is a root 2 by 2. Okay, so it is slightly distorted. It is not exactly octahedral, it is slightly distorted. Okay. so this is an octahedral void. Okay. Now you can also have a so you have a distorted octahedral void. You can also have a distorted tetrahedral void in a BCC structure. So and that's easy to see. You take the atom from this this cube, you take the atom at the body center of the neighboring cube. Okay, so this is in the neighboring cube, and then you take these two atoms, okay, and you will get a tetrahedron. You will get a pyramidal structure, and at the center of this polyhedron is a tetrahedral void. Okay, so this is a distorted tetrahedral void. Okay, now I'll just mention that the octahedral void, okay, the radius. So for this, R void of this relative to the R of the atom is about 0.155, whereas for the tetrahedral void this same ratio 0.29. Okay. Now I will leave it as an exercise to you, okay, to show where the voids in HCP are, but you can have both HCP also has a octahedral and tetrahedral voids. Hedral voids, okay, and this is left as an exercise, okay. So I'm not going to work it out explicitly here. Okay. So the point that we have been talking about is that if you look at the space available in a void, so for FCC we saw that R void, this is for the tetrahedral void. So R void divided by R atom, this is equal to 0.225. For octahedral void, okay, we said R void divided by R atom, this was actually 0.414. Okay. So what it seems to suggest, that if you had a different atom, if you had an FCC lattice and you had a different atom, okay, that was much smaller, whose size was 0.225 that of the FCC atom, okay, then it would fit into the tetrahedral void. Similarly, if it was 0.414 times the size of the FCC atom, it would fit into the octahedral void. Okay. However, in practice, we see much larger atoms go into voids. Okay. And this really again goes back to the idea that atoms are not spheres, are not hard spheres. Okay, they distort, they can actually stretch out they can push the, so you can put a bigger atom into the tetrahedral void in FCC by pushing out the atoms of the FCC. Okay. So I will conclude this lecture here for now. Okay. This is a slightly long lecture, okay, where we have talked a lot about coordination number and voids. Okay. Now in the next few lectures I want to start talking about the different kind of defects that you can have in crystals. Thank you.